Hello everyone, I'm Abid Ali and today I'll be presenting MULSUM, a multimodal summarization system with Vis-Aligner and diversity-aware image selection. This is a joint project with Tiago Mola and Usman Naseem at Macquarie University, Sydney. Current multimodal summarization systems face two linked problems. First is token inefficiency. Many methods pass all the image patch tokens directly to the Fusion modules, and with the increasing number of images, the costs or the sequence length grows quadratically, which is a serious problem. The second problem is the visual redundancy. Once the summary is generated, even though the summary quality is really good, the selectors mostly select the images which have higher relevancy with the generated summary. And with this approach, the systems end up selecting all the images which are near duplicate, and this limits the usefulness for end users. More on that computational side, in early Fusion systems, all the image patch tokens are connected with the text tokens at the very first transformer layer. And with this approach, as with the increasing number of images, the length of article grows sequentially. And moreover, recent token pruning studies have demonstrated that up to 90% of visual tokens or patch tokens can be dropped without affecting the downstream task quality. So the question for us was really simple. Can we use only the limited number of visual tokens without compromising the summary quality? On the quality side, since after the summary is generated, the model selects the images, and if the image selection process is carried out with respect to the relevance with the summary, the systems end up selecting visually similar images. For example, if you look at both these images on the left and the right, the images almost appear similar with a slight view difference. So for the end users, these images will appear as near duplicate images and are not contributing much towards the overall utility for the users. Okay, so once the we have established the motivation behind this work, now we can talk about the architecture. Mulsum is a two-step architecture. First, Vis-Aligner is used to encode the visual information or visual cues before conditioning the summary generation. And once the summary is generated, the second component, which is our DAR image selector, it selects the images which are similar to the summary as well as these are distinct within a set. We'll talk more about this DAR approach in the upcoming slides. More on that Vis-Aligner, in our approach, instead of using all the image patches, take a frozen clip CLS embedding. That is basically the overall embedding that is used to represent the image. So we use one CLS embedding per image, and then we project it into the same embedding space as the decoder, which in our case is Llama. So this way, basically, we are not using any deep fusion or cross-former attentions to learn the visual information. Rather, we are just using a simple linear mapping to project the image features into the same compatible space or dimensions as we have the text. Okay, and this is very important to understand that why are we using this simple linear mapping instead of those deeper cross-model transformers to learn a joint space. With this approach, where we are projecting the image features into the text dimension with a simple linear mapping, we are preserving the textual information intact up until the point of the decoder. Because if we combine both the information at the very start and then perform that cross-model learning where we are trying to combine the image and text features, that way most of the times the model learns to rely only the text modality, that is the text is the dominating component, as well as sometimes the model might learn to ignore the visual features completely. So in order to address that, in this case, we are ensuring that text does not dominate or does not have the same opportunity to ignore the images up until the generation step. Okay, now on to our second component, which is DAR. We name it as diversity aware relevance. This approach is inspired for maximal marginal relevance, which is used a lot in the information retrieval systems. In our situation, the intuition behind using this MMR based approach is that, first of all, the each image which is being selected should be similar to the summary, as well as whatever images we are selecting as part of the image sets, those images should be distinct to each other to ensure that we have a diverse set of images. In this case, lambda is a tunable parameter which, based on our experiments, we set it to 0.7 to balance between the alignment between each image and summary, and also the diversity between the selected image set. And since we are using the shared space embedding, that is which is obtained after projecting the image features into the text domain, so instead of re-extracting the image features or using the clip another time, we just use the same projected image features or CLS projected features in order to calculate these similarities between summary and the inter-image set diversity. So this was our architecture. Now we can talk about the data set on which we evaluated our system. So to evaluate our systems, we used the standard MSMO data set, which has been in action for about 7 years now and is kind of a de facto standard, or one of the go-to options if someone is working in the domain of multimodal summarization with multimodal output using image and text. And the standard dataset MSMO is crawled from Daily Mail dataset, Daily Mail news articles, and on average there are roughly 650 words in each average, and each 650 words in each article, and each article on average has 9 images along with the news article. uh, as in terms of labeling, we have the textual summaries available for whole data set, whereas human annotated representative images are only available for the test data. Uh, in order to evaluate the model, we relied on Rouge to calculate or to evaluate the text quality or text summary quality. We relied on image precision to calculate the visual relevance, and in order to evaluate the multimodal quality, we use this multimodal automatic evaluation metric, which is another standard evaluation metric being used in this specific domain. These are the results, and as you can see, our proposed systems MULSUM achieved highest scores in terms of the text quality, which is greater than the Wilson, CETA, and UniMS models, all different kind of architectures, and these were the best previous state of the arts. And if you look at the multimodal quality, you will see that the multimodal quality evaluation matrices, including that image precision and MMAE, are not beating the previous or not beating the existing scores. And this was a kind of a deliberate choice, because instead of selecting all the images based on the similarity, we have added an additional component to enhance the user utility by ensuring that the selected image set is diverse at the set level. We'll talk about this diversity factor more in the next slides. Okay, though we achieved higher text quality scores and comparable multimodal quality scores, we did a few ablation studies to evaluate whether the improvement we are getting, is it purely based on the images, or is it just due to the additional extra parameters we have introduced in that Vis-Aligner. So our full system achieved an accuracy of 44.75, but when we did not pass any input images to the system, the Rouge score was comparatively low. And then we did another test where instead of passing real images, we just passed some Gaussian distribution noise data as images to the model. And the results were interesting and were really helpful to conclude that our system was able to distinguish between irrelevant images, or it learned to ignore the images if images are not helpful for the summary, and we achieved more than 1% improvement in terms of rouge when using our full system with Vis-Aligner, which which uses or represent each image with CLS and then projecting it into the text dimension. Second test we did, we compared the automatic metrics with both approaches. The first approach was similarity only, where we selected the images based on purely similarity. Because in this test, our goal was to identify that our additional attribute, which is diversity, when we introduce diversity, does it impact the standard automatic matrices, including image precision and MMAE. So in case of the images which were selected based on purely similarity, we achieved comparatively higher image precision and MMAE. And with the diversity attribute considered, or with DAR based selection as expected, we were losing some performance in terms of those automatic matrices. Okay, so though in terms of automatic matrices we were having lower scores, the next thing for us was to evaluate whether this diversity attribute is helpful for users or not. But before testing that, we looked at the images, and this is one of the examples. So based on the similarity based selection, as we can see, all the images are basically the same and looks like the wider shot of the stadium itself, whereas our DAR based selection, the images which are selected with DAR shows one image with to represent the in-game action. Second image is showing the crowd atmosphere, whereas the last image is showing the post-match outcome. So instead of displaying or selecting all the similar images as done in the similarity only baseline, DAR was able to select a diverse set of images which can be mapped to the semantic diversity of the summary to address different points. So this was just the qualitative observation. We also did human evaluation to verify that whether our diversity or DAR based approach is actually good or not. And results were as expected. Our DAR based image selection was ranked 13% more helpful by human users as compared to gold standard labels which we had in the MSMO dataset, or the similarity only selection. And in these human ratings, we ask them to rate the image set on a scale of 1 to 5, Likert scale rating. So based on the two bottlenecks we identified at the start of this presentation, our MULSUM systems was able to achieve both the goals, or was able to resolve both the bottlenecks. First, the Vis-Aligner proved that if we project a single CLS token per image, we can achieve a state-of-the-art text quality scores, whereas on the quality side, DAR shows that the MMR inspired diverse image selection is rated higher, or is given good scores by the humans, and it's more satisfactory or more helpful in terms of the user experience. And to conclude our work, we can say that the future of multimodal summarization does not require compute or deep computing. Rather, we can still use the lightweight modality mapping, and also we can penalize the visual redundancy in order to achieve the true user experience. With that, you can scan the following QR code to check out the code repository for this project, and I would really appreciate if you could connect me using LinkedIn QR code. Thank you so much. Now you can ask your questions.